Hello students, our next topic is Gauss Theorem in electrostatics. In this topic, we actually apply the knowledge of the flux that was developed in the earlier topic. Remember students, Gauss Theorem is applicable for Gaussian surfaces. Any Gaussian surface is a closed surface. So surface that you consider should be a closed surface. For example, any closed volume like cube, cuboid, cylinder, sphere, these all are Gaussian surfaces. So this Gauss theorem in electrostatics is applicable for closed Gaussian surfaces. So students, to start with, let us consider a sphere having radius r and a charge small q kept at the center of the sphere. We can divide this entire sphere into smaller surfaces having surface area delta S. So students, we can find out flux through this small surface delta S by the equation del phi equal to E into delta S. We already know the electric field E can be given by kq by 4 pi. We already know that the electric field can be given by q by 4 pi epsilon naught r square. So we can write it as 1 by 4 pi epsilon naught r square into delta S. We can also multiply a unit vector r cap. This unit vector is nothing but the direction from the center of the sphere radially towards the area element del S. Now from the figure we can see that the unit vector r and del S are along the same direction. So we can say the magnitude of the unit vector is basically 1. Therefore del phi equals to del S by 4 pi epsilon naught r square. Now we can find out the total flux through the sphere, which is obtained by adding the flux through all small area elements. So we can write this equation as del phi equal to summation of all del S q by 4 pi epsilon naught r square into del S. Now for the total area of the sphere, we can write phi equals to q by 4 pi epsilon naught r square into 4 pi r square. Here 4 pi r square is the surface area of the sphere. So this equation becomes q by epsilon naught. Now we can write phi equals to q by epsilon naught. So students, this particular equation gives the flux which is contained by a sphere which is having a charge q at the center. Remember students that for any closed
Tells us that
surface we
electric
will choose
flux
a
through a
normal to the
closed
surface.
surface
In
is
this
zero
figure
if
we
no
have
charge is
chosen a
enclosed
normal
by
to
the
this
surface.
surface and all the angle is found out between the electric field and the normal chosen for any closed surface. Remember students, we use Gauss theorem of electrostatics to find out flux associated with any closed surface, and in order to find flux through any given surface area, we already know the equation can be given by delta phi equals to E delta S. Now students, we are in a position to calculate the flux in a uniform electric field for a given cylinder. Now students, as you can see in this particular cylinder, we have chosen three normals because there are three surfaces. This is surface 1, this is surface 2 and this is surface 3. The surface 3 is actually curved portion of the cylinder, whereas surface 1 and surface 2 are the circular portions. So as I have already mentioned that we can choose a normal for any closed surface. And you can see the direction of the electric field as well. If you consider the flux through all these three surfaces, we can write it as follows. the net flux is equal to flux through the first surface, flux through the second surface, and flux through the third surface. Now say for this first surface 1, the flux can be E into A cos theta. Now as we can see, the flux through the first surface is actually anti-parallel to the electric field E. So we can write down phi 1 to be minus E into A1. Say this is our area A1, this is our area A2, and of course A1 and A2 are similar, and this could be chosen as area A3. So the flux is given by, say, minus E into A1. Now similarly we can find flux through the second area, which is, of course, we can see here the electric field and normals are parallel to each other. So in that case we can write down phi 2 equal to E A2 again cos theta. So in this case the flux becomes, as you can see, cos theta, theta is actually 0. So since theta is 0, we can say there is maximum flux here in this particular region. Here also maximum flux exists, but in opposite direction, so it is minus E A1. Now students, as we have seen, area A1 and A2 are equal, so we can write down phi 1 equals to negative of phi 2, simply due to the direction. Now students, for the third surface we can see the normal is actually perpendicular to the electric field E. So in that case, for phi 3 we can choose theta equals to 90 degree. So since theta is equal to 90 degree, we can write phi 3 equal to EA cos 90 degree, and that is why phi 3 will be nothing but 0. That is why there is no flux for the curved surface of the cylinder where normal and electric field are perpendicular to each other. So the third flux is 0. Therefore we can write down the net flux as phi 1 is minus EA1 plus EA2 plus 0. And since our area are same, A1 is equal to A2, in that case our net flux becomes 0. So here our net flux becomes 0. So this is what we wanted to prove, that for any uniform electric field, if a cylinder or any closed surface is kept in a uniform electric field, the net flux will be 0, considering the fact that there is no charge enclosed by the closed surface. So if there is no charge enclosed by the closed surface and the surface is kept in a uniform electric field, then obviously the net flux will be 0. Now students, what happens if we have a system of charges in which there are, say, 3 charges enclosed by the cylinder and there are 2 charges which are outside the closed Gaussian surface? So here we are considering, for a system of charges, a closed surface which is containing 3 charges, Q1, Q2 and Q3, and there are 2 charges which are outside the closed Gaussian surface. So in this case we should remember the net flux will be only due to the charges enclosed by this surface, and the outer charges will have no contribution towards flux. Now for such system of closed surface, we can find the net flux by using the method of calculus, that is phi equals to surface integral over a closed surface E into dA. So students, here we are showing area as a vector quantity. So since there are three different charges, each of the charge will produce different electric field, say E1, E2 and E3. So the individual flux could be integral of E1 dA, integral of E2 dA and integral of E3 dA. So we can write down surface integral of EDA equals to Q1 by epsilon naught plus Q2 by epsilon naught plus dot dot up to n times of the charges present in the system. And now we can write down surface integral of electric field over the area A is equal to Q inside divided by epsilon naught. So in the form of calculus, we can write the Gaussian equation as surface integral of electric field over a closed surface is equal to charge inside contained by the system closed surface divided by epsilon naught. Remember students, here when we are considering charges inside, so on the right side we have charge inside the system of closed surface, whereas the electric field on the left side is due to the charges present inside the closed surface as well as outside the closed surface. So here on the left hand side we have electric field due to both charges inside and outside, whereas on the right side we have charges only inside the closed surface. Thank you.